So this is a little bit of an experiment because obviously this is a Zoom-based Gong show, but I am very happy that I had some lovely student volunteers to give presentations to close out this meeting in the most enjoyable and celebratory way I can imagine, which is showing new physicists doing cool new physics related to what we had for this workshop. So this is the way it's going to go. I have a gong sound. Let's see, can I hear it? That you should hear when the timer goes off. It's going to be set for 7 minutes per person, and then we're going to allow 3 minutes of questioning, but I'm not going to time that so you guys can like add a lot of questions. So, okay, good. So let me start this timer and tell Adam to proceed.
Great. It's a privilege to speak here, so thanks. Today I'm talking about 2-2 scattering and the celestial torus, based on a paper of the same name with several co-authors shown here. Yeah, so let's start with a picture of the celestial torus. Then we can move on to the motivation. Yeah, so we already have Minkowski and Euclidean space. We understand lots of QFT there. So why bother studying 2-2 so-called Klein space? Well, especially within the on-shell approach to amplitudes, it kind of seems like amplitudes want to live in 2,2 signature spacetime. Specifically, 3-point amplitudes kind of serve as the fundamental building blocks, but it's usually not possible to even put them on shell in 3,1 nor 4,0 signature. But in 2,2 signature, there isn't any problem with that. You can have real on shell 3-point amplitudes then. Yeah. So we cover a number of points within the paper. Pretty much all of them touched on by Andy yesterday, but since I'm short on time, I'm just going to concentrate on the conformal boundary structure of Klein space, which despite it just being boring flat space is actually surprisingly rich. Yeah, and then particularly we find that in Klein space, celestial amplitudes live on the Lorentzian signature celestial torus rather than just some rotated celestial sphere. Yeah, so let's compare and contrast Penrose diagrams here. Yeah, so as usual, radial light rays travel at 45 degrees. That's true on both of these diagrams. Yeah, then it should also be familiar that the left edge from the Minkowski diagram is not actually part of the conformal boundaries. Similarly, that the left edge for this Klein diagram is just the spatial origin. The bottom edge is just the time-like origin. Yeah, for the usual Minkowski-Penrose diagram, each point represents a sphere. But for the Klein space diagram, the points represent tori, with one of the torus cycles corresponding to rotating between the 2 time directions, and then the other torus cycle corresponds to rotating between the 2 space directions. So that ability to rotate rather than just boost between time directions within Klein space is a pretty distinctive property, which causes, for example, that in Minkowski space we have future and past time-like infinities, but in Klein space we just have one time-like infinity, and then in Minkowski you've got scry plus and scry minus. In Klein space we just have one scry, and then still also one spatial infinity. Yeah, so let's discuss the actual geometry for the conformal boundary of Klein space. So scry consists of a null interval times a Lorentzian torus, which is the celestial torus. Yeah, then we've also got the time-like and spatial infinities, which start off as points within the conformal compactification. but it's often useful to resolve them to codimension 1 hypersurfaces. But both of them get resolved to ADS3 mod z's with the mod z factor corresponds to quotienting by a global time translation. So that they're the same geometry but with opposite signatures. One of them is 2,1 signature, the other one is 1,2. Oops, wrong slide. So topologically, ADS3 mod z is just a disk times a circle. So we've got all 3 boundary components drawn out here. Then just as a sanity check, but also to emphasize the rich structure here. Gluing these 3 pieces together should give a 3-sphere, since after all, no matter what signature your spacetime is, topologically it's just simply connected 4D space. So the boundary should be a 3-sphere. So capping on the space and time infinities to the 2 ends of scry, and then smoothing it out a little, it looks something like this. You've got a family of tori with at one end, one of the cycles shrinks, and then coming to the other end, the other cycle shrinks. So the total space from gluing these boundaries together is some closed 3-dimensional space with no non-trivial cycles. So by the Poincare conjecture, that just has to be a 3-sphere, which is a nice check. And then you can also see it more explicitly, but by noting that this construction constitutes a baby example of a toric vibration. So it's a cool surprise connection to a pretty different subject. So to conclude briefly, we were motivated to study 2,2 signature Klein space, but since 3-point amplitudes can be on shell there. With real momenta, then working out that the conformal compactification, one finds that Klein space has a Lorentzian signature celestial torus rather than a celestial sphere. There's a lot more interesting stuff to discuss, like special symmetry properties and wave functions within Klein space, but there's no time. So thank you.
You beat the gong by, let's see, 1, 2, what's it at? Yeah, okay, good. See, perfect timing. Wonderful, wonderful. Any questions? I got to make sure that it stops when it does it. It's going to keep doing this. Very good. Perfect. So any questions from anybody? It's very clean and nice talk. Yes, Luke has a question. Perfect.
Is the intention to do some analogous Wick rotation back at some point, or is it purely just to stay in Klein space? And
yeah. We definitely intend to analytically continue back to the space we live in to learn about the amplitudes we really care about.
So along that line, then, are you not introducing new singularities by going to 2,2 signature, in the sense that if you look at the propagator, like 1/p², there's no longer just soft and collinear singularities in that, but that can also go 0 at a new place now.
Like some new light cone singularities?
I wouldn't know what name to call it because it's completely new. If you just look at p² = 0, when the propagator could go on shell, or actually, sorry, it would be, the propagator would be 1/2p.k, and now inner products p.k can go to 0, and not just soft regions and collinear regions, but there's this new kind of place that a Minkowski dot product can go to 0 between two momenta, and that would obstruct a Wick rotation back. Well, that will introduce a new singularity upon the Wick rotation back.
That sounds interesting to take into account, but we might be able to make it a feature rather than a bug, since some other special like Klein space properties, like new problems can arise, but they'll serve as new constraints, and then kind of single out some special discrete set of wave functions which we think are related to these soft and Goldstone modes which turn out to be important back in 3,1 signature. So we might be able to use those as further constraints.
Interesting. Cool. Thanks.
Perfect. That was a perfect type of question and answer that I would hope for these Gong Show talks. That's a good 10 minutes about. Let's then stop sharing your screen, Adam, and switch over to Sayali Bhatkar, or pronouncing, I'm sorry. Great. Okay, so let me start the timer. Go.
Okay. Hello.
Hello. Let me know when you're ready to go, and I'll actually start the timer so I don't like.
Yeah. Sure. Okay, I'm ready.
Ready? Go.
Yeah. Okay, so today I will talk about asymptotic conservation law for loop level soft photon theorem. This is the brief overview of my talk. So these things were also touched upon by Alok in his talk. So let us start. Let's start by discussing what are asymptotic conservation laws. So this is the conservation laws take following form in the classical theory. So this is the future charge which is defined at scri plus minus, which is the u goes to minus infinity sphere of the future null infinity. Whereas the past charge Q minus is defined at scri minus plus. So now let us go to the quantum theory. At the quantum level, the S matrix has to satisfy a word identity of this kind, where the Q plus is the future charge that we discussed earlier, and Q minus is the hard charge. Now the interesting thing is that such word identities are equivalent to soft theorems. This was first demonstrated by Hay, Mitra, Porphyriadis, and Strominger, and it has been established in many cases by many other people later on. Okay, so let's discuss soft theorems. These are statements about universal statements about quantum amplitudes. So if we consider an n+1 point amplitude and take the energy of one of the photons to 0, energy which is denoted by omega, then the leading order term goes like 1 over omega. This is called the leading soft photon theorem, where S0 is a universal factor. Now in 2018, Sahu and Sen derived the subleading term in the loop level amplitudes. They showed that this term is also universal and also argued that this term is one loop exact. Now our goal is to understand if this log omega soft photon theorem is related to a new asymptotic conservation law. Okay, so we will work in this theory, massless scalar QED. The form of the S log factor, the coefficient of log omega term, it is this. Now let us note that the log omega mode in the soft expansion, that is the effect of the long range forces. It arises due to late time acceleration of particles, and this acceleration contributes to the log omega mode. So we will discuss the effect of the long range electromagnetic force on massless scalar field. This is the equation of motion for the massless scalar field. This is the free Klein-Gordon equation operator. On the right hand side, we have expanded the interaction terms at large R. So this is the leading order term at large R. AR1 denotes the 1 by R potential that is felt by the massless particles. Now we can just solve this equation and the solution takes following form. Here V and D dagger represent the free data of the scalar. Thus we see that the effect of the long range force is to introduce a logarithmic dressing of the free scalar field. This is analogous to the Padif-Coolidge dressing. Now, as a result of this dressing, the U1 current will get modified. There is a log R by R square mode in the current, so such that this mode is proportional to the dressing of the scalar field. And it should also be noted that this mode is order E cube. Okay. Now, first what we will do is we will calculate the classical radiative field generated by this modified current. Okay. So let us discuss a particular component of the field strength FRA. Around U goes to minus infinity. The expansion of this component takes following form. The leading order term is U by R square, and then there is a log U by R square mode, which arises due to the logarithmic correction to the current, and it is order E cube. Okay. Now we can repeat similar calculation at past null infinity. And what we see is that there is a log R by R square mode at the past. Now we can obtain this mode explicitly. And what we show is that this mode obey a new asymptotic conservation law of following form. So this law was first suggested by Miguel and Lalo. We proved it. Okay. Now we can construct the charge from this conservation law. So this is the charge, and y is a free parameter. Now what we'll do is we'll quantize these charges. So let me just state the result. So this charge is made up of two parts, a soft part and a hard part. The expression for the soft part is of following form, where A is the annihilation operator for the photon. Thus we see that the soft charge actually leads to insertion of soft mode of a photon, and this omega operator is such that it isolates the log omega mode in the soft expansion. Thus we see that this asymptotic charge is actually related to the log omega soft mode in the photon. So this is the expression for the hard charge. It is proportional to AR1, and we recall that AR1 is the dressing of massless scalar field under electromagnetic force. Now we just need to substitute for AR1. It is important to note that classically AR1 is 0 and the log omega mode vanishes. And we substitute the quantum expression for AR1, and it produces the soft factor S log. So this is the final form of the Ward identity. It reproduces the Sahusen soft photon theorem. Thus we conclude that the new conservation law that we discussed is equivalent to the log omega soft photon theorem. Okay, so this is the status. It was discussed by Alok as well. So we have a one loop exact subleading soft photon theorem for loop level amplitudes, which was given by Sahu and Zain. Now the memory effect corresponding to this soft theorem was discussed by Ladda and Zain. And we discussed the asymptotic, we discussed that this soft theorem is equivalent to a new asymptotic conservation law, but the symmetry underlying these charges, that is not clear yet. Okay. Yes, I would like to thank you all for your attention.
You guys are doing perfect on timing. I'm gonna let the gong expire just for the sake of showing that. Yeah, wonderful. Okay, great. So any questions here for Celia? Andy.
Yeah. So if we have the expression for the charge, why can't we just take the commutator of the charge with the field and see what the symmetry is?
Yeah. So the usual data that we have for the radiative field, if we take the expression for the soft charge and act on it, then it just vanishes. So it tells us that the usual phase space doesn't contain the mode that we need to extend that phase space to include certain modes so that these charges will have some well-defined action.
I see. So what's preventing us from, let's see, at the classical level, there wouldn't be anything preventing us, would there, for just saying we want to consider initial data that has a polynomial expansion without logs about infinity? Is there something preventing us from doing that?
Sorry, I didn't get the question. So what is the question exactly?
Well, you have things where A is going like log R over R.
Yes.
Why couldn't we, at the classical level, would be free to simply not include those things, wouldn't we?
Yeah, so you're asking what sort of modes do we need to include in the phase space? Like some, let's say some log u mode or something, such that you get a non-trivial action on the phase space. Is that the question?
Not exactly. Why do we need to consider, or why would we wish to consider situations where this charge is non-zero? And also, since it's falling off, since you've got currents that are falling off like log r over r squared, is the flux in danger of becoming infinite?
Yeah, so the usual energy fluxes, for example, those are finite. So the log r by r square mode is a Coulombic mode. So it doesn't contribute to the fluxes.
But if we have it's a Coulombic mode. I thought I saw current that went like log r over r squared.
Yes. Yeah. Yeah, so this is independent of V.
You had a J, didn't you? Didn't you have a J that went like log r over r squared?
Yes.
So if I take a zero mode of such a thing, couldn't I get infinity? Oh, this is the transverse component of J.
Yeah, yeah.
That's not in danger of becoming infinite.
Yes.
Okay, and then I guess my last question is, if there's a log, what happens to the subleading soft theorem?
That's what she said.
If there's a log term.
Yeah, so the usual the omega to the power 0 mode, that term in the soft expansion that gets corrected at the loop level. So the exact loop correction is not obtained yet. But the thing is, the log omega term will dominate the omega to the power 0 term. So this is the subleading soft theorem for loop amplitudes.
Right, but we need some need some units, right? We need log omega over some scale.
Yeah.
And so you might think that would make the subleading soft theorem, but the subleading soft theorem has been, was discovered in 58 or whatever. So why is the subleading soft conservation law well defined if there's a log term? Why is that coefficient of the omega to the 0 term? Does it make the coefficient of the omega to the 0 term ambiguous somehow?
Yes. It would generically it would become ambiguous.
I think so. I mean, this is a little bit ahead of ourselves, but if you actually do have an interpretation for how to get basically, if it was a log u behavior, like integral of log u of the gauge field, if there's a way to interpret that, then there's the structure that's appearing in the subleading soft theorems from the celestial amplitude story, where we tried to get rid of these terms, and they're contact terms only. So they're something that we're puzzled with, and we get around it by looking at the universal residue as delta goes to, I guess, 0 for the scalar, or like the appropriate value of delta. But I think there's going to be a rich connection between your story, Andy, and this story, especially once we just work out the details. So I'm very grateful for this talk.
Right. But this subject, this has nothing to do with celestial, right? She's not in a not in a conformal basis.
Exactly, but I'm like what I mean is we ran into this problem where there were log u like soft theorems that were not our soft theorems that we didn't know how to make sense of, and if some of these equations I'm seeing in this slide help us make sense of it, then there is like it resolves some contact term issues that we had in the celestial case. I'm not saying that their story needs celestial or anything like that. I'm saying that I think that this is a nice thing to have.
It's interesting that it gives this measurable power law of memory effect.
Yes.
Yeah. Thank you. It's very interesting.
Yes, thank you for your questions.
Yes, that was lovely. Another awesome Gong show, and I turned the timer off because you were great on time. So the next speaker is going to be Jose Figueroa. I think I have a longer name than that. I'm sorry if I'm truncating it.
Thank you.
Great. Say when you're ready, and I'll start the timer.
Okay. Okay, ready.
Okay.
Thank you for letting me presenting here. I'm going to talk you about a work in progress in collaboration with Julio Oliva and Marcelo Yarzo about asymptotic symmetries of spacetime modeled by Solv geometries. First, let's recap. Black hole solution in general relativity with negative cosmological constant can have spherical planar and hyperbolic horizon. And all these black holes are asymptotically locally ADS. In 5 dimensions, we can have also black holes with horizon given by S2 times S1 and given by the hyperbolic space times S1. All these geometries I mentioned are 5 of the 8 Thurston geometries, which according to the geometrization conjecture can be understood as the building block of the 3-dimensional Euclidean spaces. Interestingly, 2 of the remaining Thurston geometries can also be realized as local geometries in 5 dimensions with negative cosmological constant. And those are the Solv metric and the nil metric. And here are the metrics of the black holes, where m is related to the mass. And these black holes, I'm going to comment some features of these black holes. The asymptotic region can be reached at a finite parameter by a photon. The horizon can be compactified. The vanishing mass case define background in different sectors of the phase space of GR. And these are different sectors than the ADS sector of the theory. So it's worth to study. The asymptotic geometry is neither of constant curvature nor conformally flat, and those black holes can somehow be embedded in supergravity. I don't have time to comment on that. Now I will focus on the Solv black hole. The Solv black hole with m equals 0, with 0 mass, can be considered as a vacuum and has a 5-dimensional isometry algebra generated by these vectors. And this algebra is not semi-simple. It has an abelian ideal, so it might acquire a non-trivial central extension. So now we turn to the problem. This being a different sector of GR than the asymptotically ADS sector, it is natural to ask for a consistent set of boundary conditions that accommodate these black holes and to study their asymptotic symmetries. It is also interesting to explore the near horizon asymptotic symmetry algebra in order to compare with black holes with constant curvature horizon. Okay, so in dimension greater than 4, for ADS spacetime, the asymptotic symmetry group is the same group as the isometry group of the vacuum. And being a semi-simple algebra, it does not admit non-trivial central extension. In the Solv's case, instead, the algebra is not semi-simple, so it's worth studying whether or not a central extension appears. Now, since we are in front of a space that is neither asymptotically ADS or asymptotically locally flat, we went back to the seminal papers of Rom Genot and Genot Titelbaum and followed the procedure somehow. They proposed that the boundary condition must satisfy the following requirements. They should contain the physical relevant solution as the rotating solution. They should be invariant under the symmetry group of the vacuum, and they should make the surface charge integral finite. In order to do this, so one can constrain the boundary condition acting with the isometries of the vacuum on the rotating solution. So, and this could be done also with the slowly rotating solution. So we construct a slowly rotating black hole modeled by Solv geometry, and it's given by the symmetric and computed charge, and we could only constrain some component of the boundary conditions. So now we have to turn to study the charge for different boundary conditions in order to impose a consistent set of boundary conditions. So we use the covariant phase space formalism in order to compute the charge. I think you all know this formalism. So after a systematic study of the charge, the most general boundary condition we found were this, and notice that these boundary conditions are relaxed as compared with the ADS boundary condition, even though the charge are still finite. For example, the TT component in ADS goes as r to the -2. So that. Well, after studying the asymptotic Killing equation, we found that the asymptotic symmetry group is the same as the vacuum isometry group, sadly, as is the case for ADS5, for example. And the potential central extension is given by this expression, but since the only asymptotic Killing vector we have are the same as the vacuum asymptotic Killing the vacuum isometry, I mean, the central extension will necessarily vanish because this term would be 0. So that is sadly a plus. And the conclusion are that we have constructed a new slowly rotating black hole. The asymptotic symmetry group is the same as the vacuum isometries, and there are no central extension. Now we turn. We wonder the following question that are in progress. That is how to work out this computation in a gauge fixed approach, and if we can change the boundary conditions somehow. And also we are currently studying the asymptotic symmetry of the nil sector. That is a different sector than the one I presented here. And we have already constructed a slowly rotating black hole. And also it will be also interesting to study the near horizon symmetries in both cases to compare with the constant curvature horizon studies. And that's it. Thank you for your attention.
Thank you, Jose. Any questions? Andy has a question.
Could you just, you probably said it, but you had to squeeze a lot into a short amount of time there. What is the asymptotics of these black holes? Are they locally anti-de Sitter, but globally the boundary is?
No.
What are they?
They are not locally anti-de Sitter.
They're not.
I'm going to show the metric. Okay. Oh, I can find it's here. So the metric is not locally anti-de Sitter because of this factor that are part of the Solv geometry. So one can compute the Riemann and asymptotically does not cause as anti-de Sitter.
But Thurston was studying locally hyperbolic, wasn't he?
Oh, Thurston. Yeah. I don't know. Maybe
Thurston was discovering was looking at locally hyperbolic geometries, wasn't he? And gluing them together to get general 3 manifolds. Wasn't?
Okay. Yeah, yes, I think.
Okay, so these aren't locally anti-de Sitter. They're globally they're just something else. Is there any way to describe them?
Yes, there is something that is the work we're currently working on. So we first do the job in like the Genoa way, without gauge fixing and all that. So with all the component of the metric like this, but we were currently understanding this asymptotic geometry. So in order to do the job in a more clear way. So,
I see.
but they are not asymptotically locally ADS, so neither asymptotically locally flat. So,
And what's the topology asymptotically? What's the topology of the boundary?
It's a okay. It's a closed boundary. I think one can compactify the horizon. So, but it does not have a genus. So maybe it's topologically like a sphere, I think. That's it, yes. I have to check that, but.
Lovely. Let's thank Jose again.
Thank you for your question.
Yeah, no, this was good. And then the next person is Adrien.
Yes, hello.
So
do
I
you
think
hear
you should
me?
share, yeah, so just share your screen. I don't see your screen yet.
Okay. Zoom. Screen one. Yes, do you see my slides?
I do right now. Perfect. Okay, so tell me when and I'll start the timer.
You can. So yes, hello everybody. Thank you, Sabrina, for nice organization and for giving me the opportunity to talk to this night. So I will discuss some new aspect about asymptotic symmetries in asymptotically locally de Sitter and anti-de Sitter spacetimes, which are both relevant for quantum gravity and for cosmology, which is part of work already in progress with my PhD advisor, Geoffrey Compère, and my all-time friend, Romain Rozziconi. So what I have to say to begin, because I have to begin from one point, that the ADS case has been widely discussed in the literature, but mainly with conservative boundary conditions. So boundary conditions that prevent some energy flux or gravitational waves or whatever to cross the conformal boundary of ADS. So that leads to finite for the Dirichlet boundary conditions or trivial for the Neumann boundary conditions, asymptotic groups. And unfortunately, these kind of boundary conditions are non-exportable to asymptotically de Sitter spacetimes, because as you can see in the Penrose diagram here, if you impose too strong future boundary conditions, you will reversely back in time constrain the Cauchy problem, which is not a good feature you want. So a point that I want to stress for you today is that leaky boundary conditions in asymptotically locally ADS and DS spacetimes are really appealing and appear in recent or less recent papers in the literature. For example, in discussions about black hole evaporations that need flux in ADS that escape from the boundary of ADS and go to a flat spacetime that acts as a reservoir, as you can observe in this picture, or for example in brane worlds dynamics in higher dimension spacetime, where you can imagine some kind of holographic duality with non-trivial quantum gravity induced on the boundary of ADS. So hence the Lambda-BMS project is born with the main goal to uncover, in fact, the more natural generalization of BMS to non-flat asymptotics. And when you do the computations in that context, you can observe that we cannot have an infinite dimensional and non-trivial, I have to precise it, non-trivial asymptotic symmetry group without a fluctuating boundary structure. So the search for leaky boundary conditions in ADS or DS is in fact equivalent to the search for Lambda-BMS, what we call Lambda-BMS. I can reformulate this quest in simply finding intermediate boundary conditions that amounts merely to a boundary gauge fixing that is always reachable in any gauge by diffeomorphism, and as a consequence does not constrain the Cauchy problem in DS. So I will skip just this comment to get directly into the bulk. So the framework we used is the well-known Einstein's gravity with non-vanishing cosmological constant. And we used the famous coordinate system of Pfefferman-Graham. in the picture a bit earlier, this drawn by Starobinski also, which represent any asymptotically locally ADS spacetime as a stack of codimension 1 section on an holographic coordinate. And when this holographic coordinate reaches 0, you reach, in fact, the boundary of ADS or DS, which is the conformal boundary here, scry, that I denote by scry. With this gauge fixing, the residual gauge symmetries are while rescaling of the boundary and all the diffeomorphism that you can imagine on your boundary. And I have to review also that the solution space is completely parameterized by 2 sets of free data given on scry, a metric, and a stress tensor. So the question is it possible to define a phase space without more restriction that the conformal compactification assumption? And the answer is yes, because you can get some understanding of the benefits of the holographic normalization at the level of the phase space within the Eyerwald procedure to compute symplectic form and charges. Here is the holographically renormalized action principle, from which you can deduce the symplectic flux, morally this right-hand side, and deduce by the fundamental theorem of covariant phase space formalism the finite charges. But in fact, here you have no assumption on the flux that go through the boundary. So in general, you will get not conserved charges. And also, this flux will yield some non-equilibrium physics in which you can see the boundary metric as a source. And so you cannot expect the charge to be integrable. And indeed, the charges are not integrable. But even though this seems to be some ugly properties for your charges, you can still show that they close an algebra. But at the price that you have to modify the Dirac bracket of the charges and promote it into the now famous Barnish-Troussard bracket, which is modified to take into account the non-integrable part of the charges. And this extension is very important, as I will say later. And to finish with that point, the algebra is not even centrally extended, but is supplemented with a non-trivial two-cos cycle, which is not absorbable by a shift of the charge and reduces in the well-famous case of Brown-Hainaut boundary conditions in 3 dimensions to the Brown-Hainaut central charge. So how to get Λ-BMS? I have to speak about it now. So you have to find, in fact, an immediate equivalent of BMS in ADS or DS. So you simply, and I say simply with quotation marks, impose some boundary condition that reproduce the universal structure you need for generalized BMS in the flat spacetimes. So you demand that we have a boundary foliation, so you give in ADS a notion of time, if you want, or a notion of radius in the boundary of DS, and a fixed volume form on the codimension 2 sections of infinity. So you allow for some dynamical metric on the celestial sphere. And this universal structure is always reachable by boundary gauge fixing. You can do a counting of the parameters and you will see that I am right on this point. And so it does not constrain the Cauchy problem in DS in particular. So you are very happy with that. When you study the residual diffeomorphism of this boundary gauge fixing, you will end up with field-dependent gauge parameters because the structure equations are like that. So F and YA are the temporal and spatial components of a boundary diffeomorphism, in fact. And for those of you that are familiar with BMS in flat space, you can see that if I bring this ADS reduced to infinity, I kill this term and I am back with the standard BMS structure equations. So, but because of this term, you will have some field dependence of the gauge parameter, and as a consequence, you will also have a field dependence of the structure constant of your asymptotic algebra, which will be promoted into an algebroid rather than an algebra that we called the Λ-BMS D+1 algebroid. This will give rise to an infinite dimensional asymptotic group because asymptotic symmetry group, sorry, because you can prove that it contains, for example, the area preserving diffeomorphism on the codimension 2 section of infinity, and some explicit solutions are known around the unit transfer. To finish with this point, you can see that you can reach the Dirichlet boundary conditions, the condition that you all love a lot, simply by imposing that the dynamical metric on the section on the codimension 2 sections is now fixed, for example, to the unit transfer metric. So
your 7-minute gong. So I put another gong for 3 more minutes for your 10 minute. You have about a minute left if you want to wrap it up.
Sorry, but stop me anyways. Okay.
So if you want to take a minute to just go through whatever you want, that sounds good. But
I just want to finish by sorry, I cannot take my time right. Sorry. So we are facing with just to say that we are facing with leaky boundary conditions for this strictly greater than 2, because when d equal 2, you are back to the Brown-Eno boundary conditions, and so you can see here in the expression of the symplectic structure that in fact the symplectic couple formed by the boundary metric and the corresponding stress tensor components in fact generalize the bondinus in asymptotic flat spacetime, and the charge algebra that I presented in not so much details because I have no time encodes in fact all the information about the famous flux balance laws that you need at Scry. Yes. And if I have question about that, I can discuss also the flat limit of the Λ-BMS phase space. So please ask. Thank you for your kind attention.
Are you going to ask him the question you just asked you to ask, or you have another question?
Yeah, no, that was basically the question. My only concern was that in flat space-time, you know, a priori you have 2 BMS groups, and then you have to do an antipodal identification. So I don't see how would you get the antipodal identification by taking a lambda goes to 0 limit of this construction?
I don't see it either because it's in fact work in progress. So I have no idea how to in fact prove this antipodal identification. And I will say that with the flat limit process we discussed in our articles, it will be somehow difficult because in fact the natural matching you have is the matching through the light rays. And so you can obtain the flat limit of the phase space as the asymptotically flat phase space at null infinity, but without any information about I0. So which is the point where you will be able to discuss this famous antipodal matching. So I have no idea for the moment.
Okay, thank you.
Great, and Andy had a question?
Yeah, so it was related to Prahar's question. I mean, I think it's super important to understand how, you know, one gets BMS at the flat limit of ADS, because at some level, the holography we'd like to understand in flat space should go over to the, you know, we don't really understand how that should happen. And related to that, is there different kinds of asymptotic symmetries and conservation laws that people discuss? So, you know, BMS originally had a BMS in the future and in the past, but there were sort of conservation laws that in the GR community, people like to talk about a conservation law where the change in the BMS charge of the body mass aspect is equal to the related to the flux of the news and so on. But that's a different kind of conservation law than you know, there's some charge associated with the incoming data that's exactly equal to the charge going for the outgoing data. And in order to have a conservation law, you need like that, you need to have two things, in and out.
Yes, and here I can just say what is out, in fact.
Right, but let me make a suggestion. Suppose you just take a two-sphere in the boundary of AD, or whatever, a D minus two sphere in the boundary of ADS, and you pose leaky boundary conditions to the future and anti-leaky boundary conditions to the past. In other words, you only allow stuff to come in before this surface, and you will only allow stuff to go out after the surface. And then you would expect, for example, at the level of energy, that you would have a conservation law, that the energy that came in before this surface was equal to the energy that went out. And then you might expect that to become a local conservation law all the way around the sphere. So I would think you would need one more generalization than what you've done, the leaky boundary conditions, in order to have a limit in which you could connect it with ordinary BMS. In other words, you would have to put a surface which would eventually become a surface in the boundary of ADS, which would eventually become spatial infinity in the flat limit, and have anti-leaky boundary conditions before and leaky ones after. But it looks like, the formulas that you've derived and so on are going a long way towards getting that kind of structure out.
Okay, and that may help us to understand this extended notion of bonding use, in fact, in ADS. It's your idea, more or less, or?
Yeah. And, when people get flat space in ADS3, there must somehow be a special surface I don't quite understand how that works. I understand how it works at the level of the groups, but there must be a special circle in the boundary of the ADS3 that becomes spatial infinity in the flat limit. And one could generalize that to any dimension.
Okay, thank you for the comment.
But it's yeah.
But it's something we didn't try so far.
Yeah. One other question I had is, so it's sort of, how does this work? So what you really want is, in a classical theory, the fields are all real. But when you go to the quantum mechanics, you want to include positive, you want to distinguish positive frequency from negative frequency, and that involves complexifying. I guess this was Moldacina was talking about this during his talk on Monday. So how does that work in the classical theory? How do we distinguish between you want to allow stuff to go out but not stuff to come in? That's the leaky boundary condition, right?
Yes.
But you have to complexify to do that, don't you? Or how do you do it locally? That's what's confusing. You must have said it, but I didn't quite understand how it works.
What I can say in my picture is that if I take two codimension, two sphere, in fact, at infinity, I can measure what is passing through the boundary and say, yes, some energy has gone. That I can compute, in fact, with this symplectic structure constructed on a segment, if you want, on the Penrose diagram. That I can do.
Yeah.
And in fact, we have a little problem with that. That is, in fact, this symplectic structure does not seem to be semi-negative definite, in fact.
Yes,
so
maybe if
that's
I can
also an
add,
interesting question.
Yes, if I can add something to what Adrien is saying, is that in the flux that is on the slide here, there is no sign. So there is not the analog of the Bondi mass loss formula, which tell us that we are losing mass or we are gaining mass. So we allow some flux to enter actually in the space-time with these boundary conditions. And
so
also,
it's not a one-way. It's not a one-way membrane. You're allowing stuff to both come in and go out.
exactly, a priori, there is no sign in the flux. We will have to impose additional constraint to add that.
So there's no Cauchy problem.
Exactly. So in IDS, the space-time is not globally hyperbolic, yes, because of the leaks.
I see. Well, now I'm totally confused because I thought the idea was that you still had a Cauchy problem. You allowed stuff to go out. You just didn't allow anything to come in.
No, actually, that's a good question to find what are the additional constraints we would have to impose to have only outgoing gravitational waves. But in this construction here, we have both.
Yes, in fact, I expect that we will have to reduce, to impose some additional constraint on the stress energy tensor part, because we have completely used all the gauge freedom of the boundary. So the metric is a priori untouchable now.
Okay, well, now I'm confused because you refer to when people talk about the people who do ADS holography, when they talk about leaky boundary conditions, they want to what they want to do is they want to let a black hole evaporate. That's why they're, but they don't want it to grow. So they want only the stuff to go out. And it's always bothered me that I didn't understand what the boundary conditions were that do that. But
what we can
so
say is that some
different by leaky boundary conditions. You're allowing leaking in and leaking out.
Yes, because in fact, in the computation, we observe that this presymplectic structure has no sign at scry, in fact. And we are searching for more drastic conditions that can render this symplectic structure negative as a semi-negative definite.
But then you don't even have a Hamiltonian system, right? Because there's you can't get the.
You have not a preferable Hamiltonian because the charges are by nature non-integrable.
Well, no, but that's true in the standard Minkowski space. And then there's, there's time slices. You can have a Hamiltonian which generates you long time slices, but you're saying that right there we would say that the charges are non-integrable when the news is non-zero. I assume that's the kind of non-integrability, but
yes,
but that doesn't prevent us from. Yeah, there we have in the Bondi mass loss formula, we have only contribution from stuff going out. We don't have contributions from stuff coming in.
Yes, exactly. And that's why it's missing in our analysis. I agree with you, but it's work in progress.
Yeah.
If Alok has a quick question, we can take it now. I cut off the talk so that we could make sure that this doesn't get cut off as much because I enjoy the back and forth. Alok.
Okay, yeah. Just when you take the flat space limit, so the second line that you have written that the symplectic couple goes to the shear and the news. I just wanted to, if there's a quick answer. So what is exactly the relation that in does the boundary stress tensor go to the news in the flat space limit or?
If you want a quick answer, I can just say that all is in the slide. In fact, if you compute the symplectic flux through scry plus in asymptotic flat spacetime, you see that with a factor that I don't remember exactly, but you have delta news, delta asymptotic shear with a wedge, and it's the same here, in fact. And you can see that in the solution space that the CAB in ADS, in fact, is not free as in the flat space, sorry, but it's in fact related to the GAB here. So the GAB is truly the source of some leak.
But the bracket of the boundary stress tensor with itself in ADS is very complicated, right? It's not a free field. Like the news tensor has a very simple bracket with itself.
I agree.
Nice.
You have the standard how do I say? The conservation equation of a stress tensor, and the trace is fixed. Here, when we discuss the flat limit, we do not consider such a trace because we are in 3+1 dimensions. But indeed, this tensor is not free, and the evolution equation that this tensor satisfies are in fact the DUM and DUNA of the Bondi gauge when you do the diffeomorphism.
Okay, thank you.
You're welcome.
Thank you very much, Adrien.
Thank you.
And I hope you don't mind that I cut you off on the last slide. All of your slides are available both in the room where you can go and view them, and hopefully you guys also maybe post them to the Slack channel in case people want to page through them and not have to deal with a virtual reality experience.
Yes, I will update my slides too because the version is slightly different. I will put it on the Slack now.
Wonderful. Thank you so much.
Thank you. Thank you.
Great. Okay, so our next speaker will be Bruno. Yeah, and I'll set the timer again because I'll try to be as have a harsh reputation with the timer for the actual talk, but of course I love the question and answers. So let's start sharing your slides. I think you're a co-host, so you can do that, and then tell me.
Okay. Can you see my screen?
Yeah, I see your screen. Maybe enter full screen before I.
Okay.
Great. Okay. Timer is starting now.
Okay. First of all, thank you for allowing me to speak here. So this talk is mainly based on work with Freddy, Alfredo, and Young, and also on some work in progress with Freddy. But first, a bit of introduction. So CHY formula computes 3-level massless scattering amplitudes, and this is a formula over the configuration space of endpoints on CP1 on the support of the scattering equations. And its simplest formulation is given by 2 copies of these Spark-Taylor functions like this one. And in this case, it is computing bi-adjoint scalar amplitudes. So they are known to be related to an object that is called the tropical Grassmannian 2,n. So today I'm not going to define it, but you can think of it as a polyhedral complex. And here I'm showing you a particular example for n equals 5. This would be a possible representation of it. And when we restrict to its totally positive part, which is this blue region, this corresponds to certain regions in the VHV space of metric trees, where a point in each of these quadrants corresponds to a planar cubic Feynman diagram, and each of these semi-rays as parameterizing internal lengths. So you can think of it as the space of Schwinger parameters. And in order to compute their contribution to the amplitude, we can just integrate over the space of internal lengths. So as I said, there's a relation between this positive tropical Grassmannian 2,n, also 3-level phi to the cube planar Feynman diagrams, and the CHY formula on CP1 for bi-adjoint scalar amplitudes. And in 2019, Cacciaso, Erligevar, and Miseda generalized these formulas to higher dimensional projective spaces parameterized with this K, and these are known as CEGM amplitudes. And they also pointed out a relation with positive tropical Grassmannian with the same parameter K. And there's also a notion of generalization of these cubic Feynman diagrams to what we call planar arrays of Feynman diagrams. And these objects compute CEGM amplitudes, and they're also related to the positive tropical Grassmannian, as I will explain. But first of all, what do these generalized Feynman diagrams look like? So we can take inspiration for a generalization of metric trees for the K equals 3 tropical Grassmannian as arrangements of metric trees, as explained by mathematicians in 2009. So here I'm showing you an example for n equals 6. A generalized Feynman diagram, in this case, would look like this, which is a one-dimensional array, where each element is a tree defined in only 5 particles. And each of these trees has its own metric that we can denote in this way. And when we impose these compatibility conditions for the metrics, this is very important. This is defining a symmetric tensor, which happens to be a tropical Plucker vector in the tropical Grassmannian. And well, I won't go into much detail, but after imposing these compatibility conditions, the internal lens get parameterized in some way. You can also get relations between them. And each of these generalized Feynman diagrams correspond to a facet of the positive tropical Grassmannian. So in this particular case, this would correspond to a bipyramid, for example. And we can compute their contribution to the CEGM amplitude by doing an analogous thing, which is integrating over the space of positive internal lens, not only the independent ones. And in general, for any K, we can think of a generalized Feynman diagram as a planar array, a K-minus two-dimensional array with dimensions of size n. In the diagonal entries, we have the empty set, and they are completely symmetric, its K indices. And we can completely bootstrap these generalized objects by knowing the K-1 and -1 generalized Feynman diagrams. So for example, for K equals 4, a generalized Feynman diagram would be a matrix, and each column would be a one-dimensional array of Feynman diagrams. And the CEGM amplitudes are given by summing over their contributions, which are these kind of Laplace transforms. And again, as I said, every of these objects corresponds to a facet of the positive tropical Grassmannian. So recently, Cachaso and Early introduced a formula for computing CEGM amplitudes for the canonical ordering as a single integral. So we can think of it as a Laplace transform of the positive tropical Grassmannian. And we can construct it by taking a matrix representative of a generic point in the positive Grassmannian and construct this potential function where this would be symmetric tensors that play the role of the kinematic invariance for these generalized theories. And these are tropicalized maximal minors, which are maximal minors in this positive Grassmannian, which are tropicalized by applying these substitutions. And the amplitude is just given by this integral weighted by an exponential of this piecewise linear function. So we can look for applications of this formula, and the one I'm talking about today is of theorems. So in 2019, Garcia and Guevara found that CEGM amplitudes under a soft limit, so for particle n, which is defined in this way, factorize in this very interesting way, where the leading subfactor corresponds to a standard K equals 2 by joint amplitude. So it could be very interesting to see how this leading subfactor arises from the formula that I was talking about. And to see this, we notice that the potential function can be separated into two parts, where this f hat depends on the kinematic invariants that are leveled by n. And in order to see this subfactor arise, we just have to look at the large behavior of these variables. I will explain in a second how this works. And this f hat splits into kth Catalan number regions where it becomes linear. So this is already pointing to a relation with the standard quantum theory amplitudes. So for example, for k equals 3, we take the n particle being soft. This would be possible parameterization for the positive Grassmannian. And after tropicalizing, we notice that different values for all the variables except for these two don't contribute to the leading order. So we can set them to 0. And in this case, this potential function would look, well, don't worry too much about the expression, but see that it splits into 5 regions, where each of these regions is giving a term of the leading subfactor, which up to some relabelings in the schematic invariance, this corresponds to the 2,5 amplitude. And actually, there's no need to do the integrations because we can just map the f hat potential function to the potential function that is producing the standard quantum field theory amplitude. So in the example that I was talking about, this would be the f hat, and you see that under this change of variables, this maps to the 2,5 potential function. So to get the leading subfactor, we just have to solve for the poles that appear explicitly in the 2,5 amplitude, and well, as a function of this generalized schematic invariance, and substitute them back in the amplitude, and this automatically produces the leading subfactor, and this naturally generalizes for any k. So, well, I will leave it there. I don't know how much time do I have.
You're perfect. It's going to go up soon.
Yeah.
5, 4.
Very good. Okay, thank you.
Great. So let's thank Bruno and then take any questions. I guess it's a sign of a clear talk when there aren't a lot of questions, so it's a compliment. Great. So I don't know if you've thought at all about the things that Nima was mentioning at the end of, I don't know if you were at the discussion session at the end. It would be interesting to understand how these factorizations connect with celestial holography.
Oh yeah. Well, actually, for instance, for standard quantum field theory, when we go to a physical pole, we see this bubbling picture of two spheres degenerating. And for example, for k equals 3, we get like higher factorizations into 3 pieces, for instance, or something like that. So it would be very interesting to understand if this has some physical interpretation, some kind of generalized locality or whatever it is. But I don't know about it.
Very neat. So hopefully that's a nice teaser to look at Guevara and your work and others that they were mentioned on the slides, especially because now Guevara has joined Andy's group. And so I think there's going to be some nice celestial holography overlap.
Yeah.
Thank you, Bruno.
All right, thank you.
And sorry if I butchered Alfredo's last name right there. The next speaker today is going to be Sruthi. So
all right. Can you see my slides?
yes, so I see it now. I think I'm ready to start the timer.
Yeah.
Yeah.
All right, great. So thanks, Sabrina, for organizing this. It's been a really great week. Yeah, so I'm going to talk about massive celestial fermions, which is a paper put out last September. And I should preface by mentioning that everything I did was specifically in 2 dimensions, but there's also a paper that came out at basically the same time that does this for arbitrary dimensions by Lorenzo Iacobacci and Wolfgang Muck. So if you're interested in that, you should definitely take a look. Okay, so right. So all of this background is stuff that you've probably all gotten tired of hearing over the course of this week, but the basic problem is to try to relate scattering amplitudes to conformal correlators at the 2-dimensional boundary. And the basis of this is there's a relationship between bulk Lorentz symmetries and boundary conformal symmetries. And conformal primary wave functions have proven useful for making this connection. There are single particle scattering states for which the plus 2-dimensional S matrix elements transform as D-dimensional conformal correlators. So we've been able to do this for scalars, for massless particles, and also for massive bosons, as others have talked about this week. And so the natural way to generalize this is to say, can we do it for massive fermions? So that's the basic problem we're trying to solve here. In particular, just some conventions, which you're also probably familiar with. Massive momenta are parametrized by y, z, and z bar, and a mass where y, z, and z bar are coordinates on these hyperbolic slices. Null momenta are parametrized by w and w bar, which are points on the celestial sphere and an energy omega. And we'll use this infinitesimal Lorentz transformation in terms of the regular SL2C transformation parameters, as Michael mentioned in his talk yesterday. Okay, great. So the first thing we have to do is propose an ansatz. And this is very similar to what Michael talked about yesterday. It's basically the same form with a couple of different changes. In particular, this U here is in terms of the spinor solutions to the Dirac equation. And what we do is we say that we want this bolded G in the middle equation to transform appropriately under Lorentz and conformal transformations. And this gives us 6 differential equations that we can solve, and then they're further constrained by asserting that they're solutions to the massive Dirac equation in 4-dimensional space. So now we can use these wave functions to construct a basis, right? So first we get these solutions. They look as follows, in particular in terms of these phi1 and phi2 here, which are just 2 spinors. And they're not linearly independent. They're just all the solutions to these equations. And this massless limit is also consistent with what Fotopoulos and others talked about in their paper about the extended super BMS algebras. So now we consider an inner product on the space. In particular, we talk about the Dirac inner product because we're talking about Dirac spinors. And we get this formula, which has a lot of terms, but in particular, it has one term that's proportional to a delta function and one term that's not. And we want to assert that these wave functions are delta function normalizable with respect to this inner product in order to determine what our basis elements are. So basically, we want to pick out this first term in the inner product, and we get two basis choices. One is where we pick all of our wave functions to be j equals a half, and then we have to pick lambda to be the whole real line. In particular, sorry, the convergence of this inner product constrains the conformal dimensions to be on the principal series. So delta is constrained to be 1 plus I lambda. And in this first case, this second term will always be 0 since j is equal to j prime. Our second basis choice is where we pick j to be plus or minus 1/2, but we restrict lambda to be larger than or equal to 0. And in this case, the second term will also always be 0 because the delta function lambda will never be satisfied. Now, what we can do is we can construct an inverse transform to the plane wave basis, which is just basically an exercise in trying to figure out some integral identities that work out really nicely. And then we can write down what the plane waves are in terms of the scalar bulk to boundary propagators and these spinor solutions that we found previously. All right. What are some important properties of these wave functions? Well, we can take the shadow, and we find that the shadow appropriately flips the spin and also takes delta to 2 minus delta, which is what we expect. We can also do what others have been talking about, where we transform 4-dimensional scattering amplitudes to celestial amplitudes. In particular, it looks something like this, where this A tilde is a celestial amplitude. This A is the momentum space scattering amplitude, and these U's are some linear combinations of these spinor solutions, which you can solve for by just taking appropriate inner products. Okay, we can also find what the momentum generators look like, which means we want to solve the eigenvalue problem. And Michael talked about this in his talk yesterday. And in particular, the fun part of this is that the momentum generators take this particularly long form, but they are exactly what they got in their paper for just spin 1/2 rather than the integer spin. So there's no difference in what these momentum generators are. And in particular, if you look at them along with the Lorentz generators mu and u, they form a representation of the Poincare algebra. And so in particular, you could use these momentum generators to try to find constraints on celestial amplitudes and other such things. Okay. What I thought was probably the most interesting part was that the relation to higher spin wave functions. So in particular, I can look at the spin 1 wave functions. And these are what they found in this paper by Zlotnikov and Law on massive spinning bosons. And these things in here that I've highlighted right now are written as linear combinations, or I guess, yeah, linear combinations of tensor products of these spinor solutions that we found. And they are exactly equal to the polarizations that appear in the integral expressions for the spin 1 wave functions. And the relation between the two is precisely just the Clebsch-Gordon coefficients, which is why you have this 1/2 in the middle one. And so what you can do then is construct, for example, the Rorita-Schwinger wave functions, which are just massive spin 1/2. And you can show that these are what you get for the U's. And in principle, what you could have done is what we did for spin 1/2. You take this ansatz, you plug it in, and you solve for what these U's are. And you can show that these are exactly the U's that you get. They transform appropriately. And they're also, again, the Clebsch-Gordon coefficients, which is normalization. And in fact, the massless limit also agrees with what Taylor and others got in their paper. Yeah, so okay, we have an explicit form of these Dirac-confirmed primary wave functions. We figured out how amplitudes containing fermions will transform from momentum space to the celestial basis. The shadow flips the spin, and it also takes delta to 2 minus delta as expected. These wave functions are delta function normalizable, and in particular, we have two complete bases we can choose. The momentum generators have the same structure as integer spin, and higher spin wave functions can be written starting from spin 1/2, so we can construct the entire tower. Thanks.
Wonderful. I like the duck too. Any questions? I know that when this paper came out, it was a very lovely paper, and it definitely was useful to us looking at massless in particular. So thanks, Sruthi, for that work. Anybody want to ask more about that?
I have a question.
Yes.
So now, for example, here you say higher spin can be written starting from j equals 1 equals 2 using Lebesgue-Gordon. And you gave us example for 3/2. So what when you want to go for, to consider 5/2, for example? Is it some recursion relation? Where do I see it? I mean, did you maybe look at it?
So I didn't actually look in particular at spin 5/2, but basically what you can do is you can make the appropriate combinations between I guess for 5/2 you need to make the combination between like spin 2 and spin 1/2, and you can make the appropriate combinations where the prefactor out front is just the Lebesgue-Gordon coefficients, and you should get your spin 5/2 wave functions as well.
Okay.
I didn't explicitly check it though, but
no, I mean, from the way you say it, I see it can be constructed, okay, but I mean, like, can I write it somehow compactly and say, okay, I just need to insert now my number, and that's it. I mean, I would guess yes, right? So I was just wondering, maybe you consider it, okay.
Yeah, I think you should, so you should be able to, so, oops, okay. Yeah, so like here, right, I have, you can write down, you know, these U3/2 in terms of so these epsilon 1s are the polarizations for the spin 1, and then the U/2 are the spinners for the spin 1/2. So in principle, I could also write down, you know, this epsilon 1 as I've written it on the left, and then you would have an expression for U3/2 solely in terms of these U1/2 spinners.
Okay.
And yeah, and you should just be able to build up the same way.
Yeah, right. From here, okay. Yeah. Thanks.
Yep.
Wonderful. Scott has a question.
Yeah. Are half integer spins problematic at all from the point of view of the boundary correlators? Like in 2D CFT, we have to, you know, GSO project to integer spin for modular invariance, stuff like that.
Mm-hmm.
Is there anything like that here?
That's a good question. So because I didn't actually compute any correlation functions in particular to check whether this makes sense, I don't actually know whether you would run into any problems there.
I mean, amplitudes involving like space-time fermions are surely well defined.
Well, yeah,
the question is whether there's whether there's something basis.
Right. And I'm not sure what happens exactly if you decide to just take I thought about taking some simple momentum space amplitude containing fermions and transforming it, but you know, because these are massive fermions and you have to deal with these bulk to boundary propagators, you know, in general, it's a pretty heavy computation to get into, and I was convinced that there shouldn't be any issues there, but that's a good question. So it might be worth it to look into it and see if there's any issues that arise there.
Yeah, and there's like soft theorems by Taylor and I think Seeberger and others where they make sense of the gravitino current.
Right. Yeah, that's right.
This type of construction where it becomes a lot simpler when it's massless because everything just becomes like the spin frame products, but in the same spirit of your Lebesgue-Gordon thing right now. And
shouldn't we expect, I haven't really thought about this before, but Scott's good. Shouldn't we expect that if we exchange two final state fermions that we get a minus sign in the S matrix?
You get a sign from the shadow too, like the shadow squares to -1.
Yeah.
And also one thing you do see in the massless case, at least, there's this funny branch choice that like comes about that's a little bit weird because there's like a 1/square root of q dot x. So depending on where you are in x, like there's this funny sign that could come from in and out. So that might be related. Like how, yeah.
Yeah, like at the very, like in CFT, at least you want single valued Euclidean correlators. And that must map onto something.
Right, if you have two fermions in CFT, the 2-point function is 1 over z minus w, and that's single valued. But now you've got me confused, because if we had two final state fermions and we exchange their positions, we should get a minus sign, right?
Yeah, right.
She's doing it stuff at the level of the wave function right now, which is still, I mean, I think once you add the operator,
yeah, sure,
you're going to get these things.
Right.
It's a basic question. It's not like something I've spent much time thinking about.
Sure, but it's, yeah, it's definitely.
It's a basic question about like what kind of stuff is allowed in the spectrum of the
right
celestial CFTs.
Yeah.
Great. Were there any further questions? Luke has a question.
So I don't know, it is not very relevant maybe, but if you, since we have bosonization in 2 dimensions, I mean, if you, I don't know if you have thought about it, if you do bosonization of the celestial fermions, like from the space-time perspective, what kind of, what do you get? It's not very precise. Yeah, sorry.
No, that's also a good question. I didn't explore that when I was working on this, but it's definitely an interesting question to think about.
Okay, good. I think that sounds like
Thanks.
Wrapping up the question and answer. And I want to thank Sruthi again for this talk, as well as like the paper was really nice. And then let's move on to the second to last is Atul.
There was somebody before me, right?
Oh, no, oh, sorry. Actually, he's a collaborator of ours, and there was with COVID-19, there was an illness. So Yorgo.
All right, one moment. Where are you screen here? Can you see it?
I see it. Are you on your first slide?
Oops. My conclusions, sorry.
Great.
Can you see it?
I'm gonna click start.
Thanks. Okay, thanks, Sabrina. So since Lionel, my supervisor, has sort of inflicted enough twisted theory on you for today, I'll talk about some much more basic work on celestial OPE that I did in collaboration with 2 other PhD students, Stephen Umbert and Dian Wang. So as Anna explained yesterday, the celestial OPE can be identified with collinear limits of gluon and graviton amplitudes. And it basically captures this particular 2-particle factorization singularity corresponding to K1 plus K2 squared. And we have also seen in the second paper here that the collinear singularity can be holographically predicted completely by using the subleading soft gluon symmetry. But collinear singularities are not the only kind of singularities that flat space scattering amplitudes have. Famously, they have factorization singularities, which are necessitated basically due to locality and unitarity. These are basically just propagator singularities, on top of which, if you take a residue, then the amplitude factorizes into 2 smaller left-right subamplitudes. And the precepts of conformal field theory also tell us that in the celestial correlator interpretation, there should be some sort of gluing map, as Andy mentioned, or some sort of an operator that you can insert that basically encodes insertion of a complete set of states that factorizes the celestial amplitude into 2 celestial subamplitudes. So can we hope to sort of probe factorization singularity through the celestial OPE? So one way to do it would be by the conformal block expansion, but that's hard and I'm not a CFT person. So I'm an amplitudes person. So I decided to go to a much more basic idea to sort of generalize the collinear limit of 2 particles coming collinear to a multicollinear case. What this automatically does for you is it sort of recursively probes all the factorization, all the propagators that I've drawn in red here, because they all go on shell simultaneously because they all involve only the collinear momenta. And at least for gluons, it has been shown that this has a universal structure where a capital N point momentum space amplitude factorizes into a bunch of splitting functions, very similar to the two-particle collinear limit and smaller subamplitudes. For gravitons, we don't have any such results, but I can mention that later if someone asks me. So the hope is to sort of probe these multicollinear singularities and probe the factorization singularities and build some sort of an Escher painting-like picture where you sort of reconstruct the amplitude inside the bulk as you expand in the OPE. So how would you hope to, so here's a bubbling picture, as somebody mentioned, Bruno mentioned, I think, whereby you can hope to get the factorization, get the multicollinear singularity by using the OPE recursively in some order. It gives you up to a color ordering. You basically take the OPE of the first two particles, the first two operators, whatever comes out, you take the OPE of that with the third operator, and so on until you've taken all of them into account. And the question is whether this can match a Mellin transform of the splitting function. So here's a sort of flow chart of how this might give us a sort of a two-pronged test of celestial holography, wherein on one side, you could try to do perturbation theory, determine the multicollinear limits, Mellin transform, but on the other side, you can conjecture that they come from a celestial OPE, where I've put bootstrap in quotes because I'm only going to use symmetry constraints, but in future, you could try to do anything you like, associativity and stuff. And you can hope that these two procedures would give the same answer. So we took some baby steps towards this. We haven't succeeded a lot, but we have succeeded in getting the next sort of interesting singularity beyond the two particles, Z1 minus Z2 singularity. So just quickly, here are some results for the celestial OPE coefficients that we found. So we just restricted our analysis to finding OPE coefficients of conformal descendants, which can be recursively constructed using a procedure developed by Banerjee, Ghosh, and Gonzo before us by using just the supertranslation. So global supertranslation, I just mean the Poincaré translations. Using these, demanding that the OPE be closed under these global translations, you can fix the OPE and using the seed OPE at the leading order, which is just the beta functions as boundary conditions, you get recursion relations, and that allows you to fix the OPE coefficients of conformal descendants. So I'm not going to need these extra OPE coefficients of mixed conformal descendants because they end up dropping out. I'm only going to use these, and so I have a test of at least these OPE coefficients, that's why I flashed them here. Okay, so what do we have? An example.
We have a mid-talk question, so that means I'll extend your time. Andy, do you want to ask it?
Yeah, I'm a little confused. Isn't the bottom stuff in purple? Doesn't that all come just from standard SL2C? What does it need? Why does it need translations?
It's just easier to get at using translations. If you use L-1, actually, in a normal conformal field theory, you don't get these OPE coefficients. You get more complicated OPE coefficients if you just use L-1 constraints. But due to these extra translation constraints, those OPE coefficients sort of simplify. And they're like much nicer here. And you can determine to all order.
I see. Let's see. We could get them just by replacing the primary with the conformal block, essentially, right?
Yes, yes, yes. They are exactly.
But you're saying that that gives you a complicated formula, which you then simplified using translations?
Yes. There was another reason why I didn't use L-1s, because in general, this OPE will also have Kac-Moody descendants, and L- and the conformal generators have a non-trivial commutator with the Kac-Moody currents. But the translations simply commute with the Kac-Moody generators. That's why I could use translations and not worry about mixing in with the Kac-Moody descendants. We have an example we have at least one sort of example where we use L-1 constraints, and we have to simultaneously put a Kac-Moody descendant to sort of get a consistent solution for these OPE coefficients. So that there were two reasons for this.
I see.
Simplicity, basically.
I'm going to resume your time now.
Thanks. So just an example. Well, basically, this is the most complicated sort of thing. This already shows all the complexity of what we were able to do. In the 3-gluon case, you can take the, so the 1 + 2 + 3 plus going to some gluon is very straightforward, just gives you the leading beta functions, doesn't probe the subleading OPE coefficients. So this is the first interesting example. In the 1 - 2 + 3 plus going to, if you have a negative helicity gluon on the other side, this also has a very simple structure, which just gives you a pair of beta functions on Mellin transform. So that also doesn't probe any factorization poles. Instead, these two extra singularities, so 1 - 2 + 3 plus going to a positive helicity gluon, PE plus, probe these particular extra singularities. So they have these Z-bar1 to Z23 and Z1 to Z-bar23 singularities coming from the OPE, but they also probe these somewhat more interesting singularities. So in #1, I have a singularity, which is not yet a 3-particle factorization pole. But it's somewhat more interesting nonetheless. It's actually secretly a 2-particle factorization pole, where one of the particles is the third gluon, and the other particle is this initially virtual gluon that has now gone on shell. So this is just a 1/3p singularity, which gives like a toy case that you can try to develop before you go to the more complicated monster. But #2 does see the 3-gluon singularity. And we haven't been able to determine the full singularity using just conformal descendants. But even here, if you do a sort of leading order approximation, where you expand in the parameter in the ratio of the holomorphic distances, the leading order part that you get is still going to be completely fixed by the conformal descendant OP I showed you before, because it has the same, miraculously, it has the same form as this, the other case, up to a complex conjugation. So just quickly, #1, you can Mellin transform and you get the beta functions that you expect, just the product that should appear in consecutive OPEs, and a 2F1 in this ratio. This ratio is like the actual variable that the 3-point OPE should depend on. And we can get this from the OPE coefficients. Simply take the OPE, do the first contraction, keep the descendants. In the second contraction, you only want one gluon because that's the state that's flowing in the final subamplitude. So you only keep the leading order gluon. And the only thing now you want to compute is the action of this descendant on Z23, and which you can compute. As I claimed earlier, since the singularity is 1 of Z23, the D2 bar derivatives don't contribute up to contact terms, which I neglected here. And the rest of the terms sort of, you can calculate and show that this is exactly the standard 2F1 hypergeometric function series expansion in Z12 or Z32. And so this like holographically generates that 2-particle 3p singularity for you. And the other OPE coefficient sort of generates this other sort of leading approximation for you by the same analysis. Yeah, similar analysis approximates the other singularity by yielding a 2F1 in the complex conjugate distance ratio. Here are some suggestive notes that I've put in. Actually, the other singularity, you can expand instead in Z-bar12 and Z-bar32. And you have a very beautiful structure here. Even this seems to be expandable in terms of these higher order linear poles. And when you Mellin transform, you just get more complicated Motor-Gelfand hypergeometric functions. So something that I'm taking away from this conference is that you guys are seeing these higher n equals, higher delta modes in your conformal block expansion. And I don't know what they are yet. There might be Kac-Moody descendants or translation descendants of some sort. But my hope is that if I can determine the OPE coefficients through some recursion relations, then I might be able to predict the full 3-particle factorization singularity. But that's more or less the work in progress here. Though we
to be
already
fair, I need to cut you off now, but I have a hard time doing
I'm
this.
done. I'm done. So here are some future directions that we're sort of pursuing. This like Kac-Moody descendants, things I told about the OPE double copy, which I have discussed with Andrea yesterday. And there's some work that with Tim Adamo and Eduardo Casali that is on a shelf to relate celestial OP and ambitous string vertex operator OP. And there's some work with, we just started some work with Anders Schreiber and Matteo Parisi on Grassmannian things because these factorization structures, the kind of hypergeometric functions that occur, they naturally have Newton polytopes and stuff associated to them. So there might be some insight there to gain. And finally, with one of my collaborators on this thing with Dian, I'm trying to sort of bootstrap this for just SD Yang mills, because I have like a connection with MHV rules that I can mention if someone asks me.
Yeah, and then these
it's easier because title.
So it's nice. Yeah.
Okay, thanks, Sabrina.
Yeah.
Sorry about
no, thank you so much. No, this is very interesting. I'm trying very hard to be fair and cut you off like I cut everyone else off, but okay, like it's very interesting. So thank you a lot for this talk. Well, I guess first a round of applause to thank Atul. And then let's ask, I guess, Prahari a question. Let's ask.
More like a comment, since we were discussing this earlier. The formulas that you have for the OPs, these
suggestions, I'd be very happy.
These singularity structures are incredibly similar to the ones you get when you do simultaneous soft limits. I really think it's like a short step from your results, perhaps, to really understand simultaneous soft limits. I think that would be a very interesting thing to explain.
When simultaneous, do you mean like 3 or higher?
No, you take two gluons, let's say, the simplest example, you take two gluons to be soft simultaneously. So you have their energies to be proportional to each other. You keep that proportionality fixed, and then you take both of them to be soft. And this is a much more complicated type of soft theorem. If the helicities are different, you find a much more complicated type of structure. You get extra poles. And many of those poles, I think they look so similar to this formula that I'm seeing on your slide right now.
That's because these poles are universal due to MHV rules.
Yeah, that's and the soft theorem is universal. So
yeah.
I think it should not be that hard to just derive the simultaneous soft theorem using. So the idea that I was having was that you mentioned you sort of inserting some basis of states. So the idea that I had was, what if you insert a basis of states in between the two gluons that are soft? So now I have two separate amplitudes in which each of them are single soft limits. We know everything about single soft limits. And so perhaps all of these extra poles are then coming from just the completeness relations that you have to input when you do this, because then you can reduce a simultaneous soft limit to two single soft limits. But with complicated, you have to do an infinite sum over all the full completeness relation, and then you might.
I thought that if you want to insert a complete set of states, you will sort of fall upon conformal blocks.
Exactly. So it seems to me that you've done most of the heavy work, and I think if maybe just a bit more.
Yeah, I mean, yeah.
Okay, this was confusing me. That's why I went the multicollinear way instead of the.
Yeah, because in celestial CFT, we make sense of the collinear limits first, and then trying to interpret residues at different delta would be harder to then reconstruct with Prharsing. But that's interesting, yeah.
I'm happy to talk if this can be made work. Yeah.
Yeah, regarding your last point about the self-dual, I mean, like these conformal primaries are set up for that already. So if you can do some sort of like perturbation on top of a single insertion, that's harder or something. That's good. Oh, wait, Andy had a question.
Yeah, could you just try to, I mean, I saw where you had it in the question, but could you try to just say more generally what you mean by your first point, that you can see 4D physics emerging from 2D physics?
Oh yeah, basically this is the basic test that I try to do. That if you have O1, O2 up to ON, use the OP O1, O2, get C1 to K1, then OK1 with O3, and so on. You can get like a sequential OP. This is the full OP, not the leading OP. If you knew the full OP, you should be able to reconstruct the complete amplitude holographically. without ever putting in Feynman diagrams of 4D QFT. But since we don't know the full OPE, we can try to bootstrap these Wilson coefficients Cij to some order using various techniques, then try to sort of give conjectural interpretations of them in terms of the 4D physics, and then try to see if those conjectures match. The two-pronged test, as I said.
Mm.
This is very interesting as well. Yeah.
Are these two sides the same?
Yeah, right.
We hope. Oh, well, it might be that only a subsector of 4D Yang-Mills or GR is determined by 2D CCFT. In that case, we'll just have to keep exploring. That's why I'm trying to explore SD Yang-Mills, because SD Yang-Mills is also integrable. There's like a lot more structure there's a lot more ease of structure, structure you can easily calculate with. And there's a chiral, well, it's chiral in some sense, the OPE algebra, even though at subleading order, you will get L-1 power descendants. Also, SD Yang-Mills has this n equals to string interpretation. So since there is a string interpretation, it might very well have some holographic dual by itself as a subsector. Actually, that's another interesting thing, right? With Chemix.
It's very natural in Klein space, by the way, the self-dual.
Yes, in Klein space.
And the operators themselves are also self-dual, like the conformal primaries that you have in their exact solutions. So yeah, lots of things.
You can use a Lagrange multiplier description where you still have positive and negative helicity gluons, where one of the gluons is like a Lagrange multiplier. But then the OPE algebra will become a chiral algebra between them. You basically just remove one of the terms in the OPE.
Great.
Thanks for the questions.
Yeah, so I think so we have one more Gong show. I think it's good to cut it here and then go to Raphaela. But of course, the floor will be open for questions, and we're all interested in it. So it's great. Thank you.
Okay.
So it's good to close out the workshop for us, which is going to be wonderful. So let me know once you get your slides ready, and I will start them.
Okay, now you should see my screen, right?
I see your screen, and
very good. Okay, great.
Okay.
Okay.
Start it. Go.
Well, hi, my name is Raphaela Wutte. I'm a PhD student at TU Wien, and today I'm going to talk about a work that I did together with Stéphane Detournay about Mervis and Gimenez. The identification of the microscopic origin of gravitational entropy is one of the most fertile open puzzles in theoretical physics. Andrew Strominger showed in 1997 that the entropy of the BTC black hole precisely matches the Cardy formula. The BTC black hole is a black hole in three-dimensional spacetime. And since the entropy can be matched by the Cardy formula, we see that the gravitational entropy can be reproduced from accounting in a two-dimensional conformal field theory. Since then, there have been many such matches between entropy on the gravity side and entropy on a putative field theory side, but many of them involve ADS3 or the isometries of ADS3, SL2R plus SL2R, or sometimes also just one copy of SL2R. And in this talk, I want to provide an example of a matching for spacetimes which do not fall into this category. Work on holography and asymptotic symmetries in general has also led to the emergence of new field theories, and one of these field theories are so-called warped conformal field theories, whose symmetry algebra you see here. So the symmetry algebra is infinite dimensional, and they admit up to three distinct non-trivial central extensions. One nice way to understand warped conformal field theories is the following. So Joe Porczynski showed in 1987 that the symmetries of any unitary translation and scale invariant quantum field theory with a discrete spectrum of the dilatation operator enhance to two copies of the Virasoro algebra. And Andrew Strominger and Diego Hoffmann showed something similar in 2011. They considered a quantum field theory with the same assumptions, but with scale invariance only in one direction. And what they found is that also in this case, the symmetries enhance, And in fact, you have two minimal options for the enhanced symmetry algebra. You either find the symmetry algebra of a warped CFT, or you find two copies of the Virasoro algebra. Now you can get back to just the Virasoro algebra by adding back the scaling in the other direction. But similarly, it's also possible to single out the warped CFT by adding a boost. Now let's come to our work. So in our work, we were focused on certain three-dimensional spacetimes dubbed warped flat spacetimes. And here you see the metric of warped flat space. So the reason why it's called like this is because it's a fibration over two-dimensional flat space. And this is a three-dimensional spacetime, which is a solution to topologically massive gravity with positive cosmological constant. And here you see the equations of topologically massive gravity, where C mu is the cotton tensor and mu is this coupling to the cotton tensor, and they have to take the cosmological constant and the coupling have to take this value such that this is a solution to the TMG equations of motion. So this metric has a constant positive curvature, but it's not maximally symmetric. And the symmetries of this metric are actually quite curious because they span the centrally extended to the Poincaré algebra. So we are in 3D, we have positive cosmological constant, and what we have as isometries are the isometries of 2D flat space plus a central extension. And here you see P2C, where P0 and P1 are the translations, K is the central extension, and J is the boost. And what one can now do is one can consider quotients by discrete identification along this combination of the killing vector. So it's a combination of a boost and a shift. And psi and omega just two parameters that we introduced when performing this identification. So you get a two parameter family of solutions. And these quotients of warped flat space were claimed to be black holes. So this is work that goes back to Musa and collaborators in 2008. And it was also the reason why we got interested in these spacetimes, because they were claimed to be black holes and had these unusual isometries. So one of the first questions that we asked ourselves was, are these warped flat quotients black holes? And to answer this question, we use a method which is called projection diagrams, which goes back to Kruschel, Eils, and Zipka in 2012. So projection diagrams are useful to depict non-block diagonal metrics with 2D diagrams. And while they are similar to conformal Carter-Penrose diagrams, there is a crucial difference, namely the diagram is not necessarily a slice of spacetime. And while they were formally only introduced in 2012, there are constructions in literature which are in the spirit of projection diagrams. And indeed, the causal diagram of the BTC black hole that is given in the famous paper by Bagnados, Hinault, Teitelbaum, and Zanelli is not a slice and fits the definition of a projection diagram. So coming back to the original question of whether these warped flat quotients are black holes, so depending on the regime of the parameters, the spacetimes either look like the left picture or like the right picture, and the shaded region in the right picture is the region where closed time-like curves start to appear. And what one usually does is one cuts the spacetime off where they start to appear, so the spacetime would look like this. So the spacetime either looks like, so the causal diagram of this warped flat quotients either looks like the one of 2D Minkowski space, or like the one of flat space cosmologies, which is kind of curious because we have positive cosmological constant. And here the dashed lines are the location of the killing horizon, which was claimed to be a black hole event horizon. So no, these spacetimes are not black holes, but they have a killing horizon, and one can associate a Hawking temperature and entropy to it, where the entropy is just the neutral charge associated to the killing horizon vector field. And the gravitational entropy looks like this. And what we did for the spacetimes was we performed an asymptotic symmetry analysis, and we found that the asymptotic symmetries match the symmetries of a warped conformal field tree, and that the gravitational entropy also fits the one of a warped conformal field tree. Thank you. And well, if you want to know more details, I will be happy to talk to you in the breakout session, or just write me an email.
Wonderful. Thank you, Raphaela. Any questions for her? A hand raised by Andy.
What is the structure of these spacetimes far from the killing horizon? Is it simple in some way there?
Far from the killing horizon. So if you go out with a coordinate row, then the structure of the constant row slices would just be the topology of them would just be R crosses S1.
Would be R cross S1. And is the S1 growing as you go out in the R?
I think so. Yeah, I should check it again, but yeah, I think so. I mean, what may be important to say is that this is, yeah, they are not, I mean, you cannot think of these diagrams in the same way as you think of a slice when you make this make a Carter-Penrose diagram.
Yeah.
If there are no further questions, let's thank Raphaela again for a wonderful talk. And that's the body of the workshop. I think right now we're going to transition into some sort of discussion session, but before that, because I know you guys have hung around for a whole week basically with me, I'd like to thank everybody who's attended, who's given talks. Thank you guys so much for making this what it is.
Well, in addition to thanking ourselves, I think we should have another round of applause for Sabrina.
Aww.